The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, ladies and gentlemen. Welcome to TechGeek webinar series, our endeavor to empower techies. We believe that sharing of knowledge is key to enhance our skills and grow us as a professionals. With this principle in mind, we have initiated a series of webinars conducted by various industry experts to give you all a crisp insight of various domains. The topic of today's session is Introduction to Machine Learning, and our guest speaker today is Mr. Kiran B. Lonikar. He is staff engineer at Informatica. Kiran is BTech in Aerospace Engineering from IIT Bombay and has done ME in System Science and Automation from IISc Bangalore. He is having over 20 years of experience in software industry in various domains like telecom, finance, internet, and big data. He has worked on different technologies, and his current passion is to use machine learning for different applications, especially in mobile apps, in order to bring it closer to the masses. He regularly keeps track of open source activities in Apache Spark and in machine learning as well. So without any further delay, I introduce all to our guest speaker. Over to you, Kiran.
Hello everyone, I'm Kiran. Thanks for the kind introduction. Let's quickly jump into the topic of today. Can you see the presentation?
Yes, we can see your presentation.
Or can you still see?
We can see your presentation.
Great. So, okay, great. So, I'm going to talk on introduction to machine learning. This is going to be an introductory talk. It doesn't involve any advanced mathematics or advanced topics. So with this, let me begin. Before we jump into what is machine learning, let's understand what's learning. So according to well-known or an earliest machine learning researcher, Tom Mitchell, learning is to improve some performance measure P of executing some task T with experience E. So in plain English, what it means is performing some task better with experience and training. Now, the key elements of this are to memorize the remember or memorize the experiences, and more importantly, to generalize from the experiences. That is what is learning. So to understand what I mean, let's observe. Let's try to see how kids learn to read words, or for that matter, learn anything. So basically, so when you teach them some words, they make mistakes even when reading from previously known words. Like for example, cut and put. You try to teach them, they would naturally try to swap put and put, for example. Then they would correct themselves, they would memorize, and then they would remember from their memory, and then they correct themselves. Now this happens. This also happens when reading with silent words or those with T-I-O-N. They would try to pronounce it as T-on, and then they would make it shun, for example. And they would apply that even to words which you haven't taught them. For example, education. If you have taught them education, they would read as education. But any other words reading in T-I-O-N, for example, punctuation, they would read it correctly as punctuation and not punctuation, for example. I'm just making this up. So with this introduction of learning, okay, so what I mean to say is by learning, you not just try to memorize from or recollect from the previous experiences, you also try to generalize from the previous experiences. So I will try to, as I said, I will try to make this as non-mathematical as possible, and let's go with that. So Now what is machine learning? Machine learning is basically to teach a computer program how to recognize different patterns. So let's go through the steps of how to build a computer program or how to build a software which learns from experiences. So there are generally 3 steps involved. First of all, you need to express the experiences E mathematically. What this means is you need to understand what the features, what the experience means, and how to express it in terms of certain set of features. For example, how to express the human voice in terms of, let's say, the various frequencies and the amplitudes present, or let's say the zero crossings in the voice. This is what is known as feature extraction from raw data. Then the next step that and the most important step is building a mathematical model. So when you build, let's say, a set of for different experiences, let's say you express those as a set of numbers, you need to build a mathematical model, or what we call as curve fitting from the experiences. In other words, we need to build a set of rules from the experiences, and then the rules need to be such that we should be able to generalize from the rules. The next, and then finally the task is to apply the mathematical model to the features of the future tasks which the model hasn't seen. So once you build a model, you apply that, you use the model to apply that to the numerical values of the features for future. You can't call those experiences, but let's call them future tasks which the model hasn't seen. And then the model will probabilistically express whether the what the task is likely to be, right? Let's move on to the next slide. Let's see what we mean by machine learning. Let's see some of the practical examples of machine learning. I'll play a video which will show a mobile app called WordLens in action. What it's doing there is it's trying to identify the text, and through the live images in the camera, right? And what you're seeing there is, what you're seeing in the mobile screen is the translated text in place replaced by the real text replaced in place by the translated text.
Sorry to interrupt you, Kiran. We are not able to see the video. I think we are facing some problem. So, can you please check it once?
Okay, maybe I'll just copy paste the link of the video. Interested people can see the video.
Yeah, right.
All right. At the end of this talk, I'll just give a link to the video. The second is a toy application I built, and that is so this application tries to recognize the letters as you scribble. Now this will be most useful on a mobile screen. So for example, if you scribble 1, can you see this? Hello?
Yeah.
Is this visible? All right,
Let's
thanks.
take a feedback from users. I think yes, it's
Yeah.
visible.
All right, great. So yeah, so let's say you scribble something. Now this will be like clearer if you try scribble this using on a mobile screen. This doesn't recognize correctly because my training data was not general enough. I'll explain that in a bit. Okay. 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 Fine. I think we'll move on. So basically, if you like going back to the video that I showed previously, what it does is from the using the camera of the using the camera, the mobile app detects, mobile app grabs the images, and then in the images it tries to locate the frames or the rectangles in which a text appears, and then so that is one level of machine learning. So that is one part in machine learning. The second is it tries to basically it tries to identify the letters themselves, and then the third is it tries to identify the letters. From the letters it builds words, and then from the words it translates the words and replaces them. So there are like 3 or 4 machine learning tasks that the application is performing like on any given frame, right? So as you can see, machine learning is a practical machine learning application builds a series of machine learning tasks rather than a single task. So with this, let's move to the next slide, where we'll talk about what are the different types of machine learning systems. The first type is supervised learning, and under supervised learning you have like several types of machine learning algorithms. The first one is classification. The second, and under so now classification, I'll explain in a bit. By classification, what I mean is, given different types of, you basically train a machine learning algorithm that okay, this data belongs to this class, this other data belongs to another class, and then when presented with the actual data, the machine learning algorithm, the model is supposed to identify which type of data it is. In regression, what we try to do is try to find how many, like what is the level of a particular output. For example, when building a weather prediction system, we need to the model needs to predict what is the wind speed, for example, or what is the temperature, likely temperature going to be in a particular region. Another type of supervised learning is recommender systems. In recommender systems, what it does is, let's say let's say there are hundreds of users who are rating different items like movies or books, and the recommender system then tries to find the similarities, either the similarities between different users by identifying the similar books that they would have rated, or and then predicting or recommending the items that they haven't rated previously. So let's say you like certain movies in the past and you rated them. The recommender system would recommend you the movies that you haven't rated in the past based on the other users' recommendations and finding out which users are most similar to you. The second major type of machine learning systems are unsupervised learning, where the data is only in terms of the features, and the features are not labeled. Like for example, you have thousands of news articles and you want to categorize them into, for example, politics, religion, sports, and so on. And within sports also, let's say you want to classify more type of like further subcategorize in terms of like cricket, hockey, and so on. So okay, so the major types of unsupervised learning, unsupervised type of machine learning algorithms are clustering, dimensionality reduction, and anomaly detection. So so we will in this talk I will cover logistic regression in classification, recommender systems, and k-means clustering. One of the earliest algorithms in clustering. So let's move on. Let's take an example of a classification task where, let's say, from the voice spectrum, you want to identify the speaker's gender. Now, as I said previously, we need to, from the voice, we need to identify certain features. So let's say the features are the dominant frequencies in the voice spectrum. Now, here I have plotted for various voice samples. I have plotted dominant frequencies, frequency and amplitude. So let's say we have labeled these. We already know that the speaker's genders here. So this is a male. All of these are male voices, and these are female voices. So from this, we as a human know that the items on the right side of this are female voices, and the items on the right side of this red line are male voices generally. But to be able to, for a machine to be able to identify this, we need to build a model. So let's say we have all of these amplitudes and frequencies. We put them as A1, F1, and G1 is the gender. This is the label of our data. Of our data A1, F1, then A2, F2, G2, and so on, up to, let's say we have M training examples. Now, the logistic, in terms of the logistic regression, the problem statement is we need to compute the probability of a gender being F given A, F, and theta. I'll explain what theta means here. It's basically the parameters of our model. Let's say the probability is some function of linear combination of A and F. Here by linear combination we mean theta 0 plus theta 1 A plus theta 2 into F. So or in vector terms it is theta transpose X, which I'll explain on the next page. So here the decision boundary, and then we can draw a decision boundary here saying if probability is less than 0.5, the gender is M, else the gender is F. Right? Now our task is to build or compute the parameters theta 1, theta 0, theta 1, and theta 2 based on the training data A1, F1, G1, A2, F2, G2, and so on, right? And so let's restate the problem more precisely here. If we say why our variable is 1 when G equals F, and y, and the decision variable y equals 0 when G equals M, and we define a feature vector called x as A and F. Let's define a function A h theta of x as, let's define this function h theta of x as a sigmoid function. Now this function is chosen for its particular properties, peculiar properties, that it varies from 0 to 1, which is what we want to model probabilities, right? So the sigmoid function is defined as, it's a smoothly varying function. It's defined as 1 over 1 plus e to the power minus z, where z is theta transpose x, which is a theta 0 plus theta 1 x, x1 plus theta 2 x2. Now this represents, this function h theta represents, h theta of x represents our probability that the gender of the voice is 1. Gender of the voice is female. So to compute the theta, now our task is to the task of this algorithm is to compute the parameter vector theta. To compute this, we need to define a cost function, which is again, this cost function has a mathematical significance. Basically we define the cost as the difference between the predicted value and the actual value. The actual value is y and the predicted value is h in some sense, because it represents the probability that y is 1. So when y is 1, let's define the cost as minus log of h, and when y is 0, let's define the cost as minus log of 1 minus h. So let's define the cost as sum over all the training examples of y into log of, where y takes the values of only 0 and 1. So here let's define the cost as sum over all the examples of y into log of h plus 1 minus y into log of 1 minus h minus lambda into sum of all the theta squares. Now this lambda into sum of all the theta squares is just to make sure that the values of theta are not unbounded. This is just so this is called regularization in terms of statistics. So now to compute the parameters theta, what we do is we use an optimization algorithm like gradient descent. You can search over what a gradient descent is. It's basically going along the slope of a curve. So basically we need to find the slope, partial derivatives of j with respect to theta, and go along the slope to find, it is mathematically known that this is a convex, the j of theta is a convex function of theta. So the gradient descent will minimize, the gradient descent will try to find a theta which minimizes j of theta. This is for a particular value of lambda and for a particular data set. Now we need to find, we need to see how the model theta x, theta performs with respect to the data that it has not seen. So then we use something called cross-validation data, which is not used to compute the model itself, and then vary the theta and then find the vary lambda and find another set of thetas for which the cross-validation for which and then find the final cost values for all the lambda values and take the lambda and basically take the theta and lambda pair for which the j of theta is the smallest. So this will give us an optimum model, and then to test our model we get the data which is not seen by the model yet, which is called test data, and then we apply h theta of x to that model and predict the gender. So basically training is a three-step process. The training computing parameters theta for a a particular value of regularization parameter and then optimizing it using the cross-validation data, and then finally using the test data. So this is computed for training data. The J of theta is computed for training data. Then using, again, I'll just recap this. J of theta is computed using the training data. So the values of X are from the training data set. Then you have the cross-validation data, and then finally the test data, right? So at the end of this, what we get is an optimum values of parameters theta, which we can now say, okay, this identifies the gender of the speaker in the best possible manner. And this is, and again, at the end of the day, this is just a probability. So basically, h theta of x greater than equal to 0.5 represents our decision boundary, and using this we compute, basically using this we predict the gender of the speaker from the voice of the speaker. So just going back, we chose a particular function for basically this decision, for this decision boundary we chose a particular function, and which is a sigmoid function. There are other algorithms in classification, such as support vector machines and artificial neural networks, which build more complex decision boundaries. And okay, we'll not go into those in this talk. I've given sufficient references for those who are interested. Let's move on to recommender systems. Here, as we previously talked, let's say we have users and items. So let's say the user 1 has recommended item 1, 3, 4, 5. User 2 has recommended item 1, 2, 3, but he hasn't recommended items or items 4 and 5 and so on. So basically the user J specifies ratings for item I. So this we express in terms of this matrix Yij, and this is what we call as our training data. Now here the features are not clear what the features are, but here there are latent or hidden features. So let's say we have K features. Now for movies, let's say we know that there could be a particular user could be rating movies based on let's say the actors or actresses in the movie, or the type of the movie, whether it's a comedy, thriller, romantic comedy, and so on, right? So, but we don't know the exact number of features. So here what we do is we say, okay, let's say we have K features. Now the feature vector for this is unknown. Let's say the feature vector is xi1, xi2 up to xik, right? Similarly, okay, now let's define another vector called theta j for a user j, which is theta 1j, theta 2j up to theta kj, right? So this represents, let's say, the weights the user assigns to each features. And then the user j's estimated rating will be theta j transpose xi, which is a weighted addition of the features. Now let's move on to okay, let's move on to the next slide. Let's say now here the problem is to learn both x and theta, both the feature. In the previous classification problem we knew x and y. Here we know only y's, a set of y's, and here we need to learn both the features and the parameter vector. So now now the task is let's define the optimization problem as minimizing the cost theta x theta transpose j minus yij for all i's where the user has rated an item. Similarly, let's define another cost term, which is theta transpose x minus yij, where for all the j's where the user has rated an item, right? So basically, we try to find the difference, the sum of squared differences, and try to minimize theta and x. Or simultaneously, we can minimize. Basically, we can minimize the sum for the entire matrix. Now, if here I have eliminated so here I have defined the cost term as the sum of square differences instead of the previous difference, instead of the log of the probability. So here, and I have also, for the sake of simplicity, I have also eliminated the lambda theta square term. So mathematically, it can be shown that if you find factors x and theta of the ratings matrix, you will basically find approximate x theta transpose will give you this matrix approximately. So wherever the ratings are defined, these values will be approximately what the user has predicted, and since the theta transpose x is going to compute, x theta transpose is going to compute the values where the user hasn't even predicted. These are the values, these are the predictions of your algorithm. Now there are different algorithms like computing user-user similarity, which are and item similarity, which are defined in Mahout. They work on the lines of, for example, from the set of recommendations, you try to identify the top 10 users who are closest to you in terms of some distance metric. So for example, you try to find the differences in ratings of different users where you have defined, and then find, and let's say where you haven't defined, you put it as 0, and then, or no, sorry, here you don't even consider, and then you try to find the users, the top 10, let's say top 10 users who are closest to you, and then based on the ratings they have given to the items you haven't rated, you would compute, you would predict your similarity. You would predict the ratings that you yourself haven't given. So again, this recommender systems type of machine learning is useful not just for human users, it's also useful for non-human users, something like Wikipedia documents. So for example, let's say Wikipedia documents have thousands of have several links, and then these links are, for example, the items, and the documents are users. So if a document has a particular link, you would say like the document has rated the link as 1, if the, or let's say the number of times the link appears in the document, and then if the link doesn't appear, you need to predict. So now based on the similarity of a particular document with another document, you would try to recommend a link to a document in order to make the document better. So which means the document's readability will improve if the document refers to or has a link of to another document. All right, so let's move from so this is about supervised learning, where you have labels and you have a feature vector. Let's try to look at one unsupervised learning example. Here, let's say you have, let's again take the example of documents, where you have where you have plotted the frequency of top 2 occurring terms in a document, in any documents across the document cluster. Here I have taken only 2 just for the sake of simplicity. There could be top n terms, and then this will become an n-dimensional n-dimensional vector. But just for the sake of visualization, assume that we are considering top two terms in across the set of documents. So let's say this is document 1, which contains let's say this is the document 1 which contains these many number of terms for term 1, this number of this many times term 1 and this many times term 2. Similarly for different documents. Now here visually we can see that these documents form a cluster, these documents form another cluster, and these documents form another cluster. The task of the machine learning algorithm is to identify these clusters. Now here the problem is we have given only the feature vector and not the labels. So the machine learning algorithm has to somehow figure out which are the documents which are closest to each other according to some distance metric, and label them as not label them but cluster them into different sets of documents. So this is how it is different from classification. So there are a number of applications of clustering in computer science. The applications are document clustering. Then you have which is used in Google News, which organizes similar news. So if you have seen Google News, it you know that it organizes similar news items from different sources under a cluster. So similarly, news clustering, where automatic news clustering, where you can identify different news items in different clusters like technology, religion, politics, and so on, or even subclusters. It's also used in social network analysis to identify different clusters of social networks. For example, you may want to identify for example, the sets of friends that you have, which form the cluster. Another application is in feature reduction, which is used in speeding up machine learning pipelines. Here, what we do is we use cluster centroids as new features. So instead of using so let's say an image is for an image is a set of pixels where the colors where the color of the each pixel identifies the pixel. Now you may have, given that you have like 24-bit colors, you may have thousands of colors, but let's say you want to identify only the predominant colors in an image. Let's say you want to represent the image the colors only in a 4-bit numbers. You would just apply clustering algorithm on the image with number of clusters equal to 16, and then pick the most predominant colors as the colors of the clusters, as basically the cluster centroid, the colors of the cluster centroids, and then use that to represent your pixel colors. So this is used. So this kind of clustered image. So this kind of compressed image, although there is a data loss, it will be used for faster processing of image in the machine learning pipelines. Similarly, it has applications in deep learning, where which is essentially artificial neural networks. And here, what you try to do is apply the supervised learning and unsupervised learning alternately. and it's also used in as a pre-processing step in recommender systems. Machine learning, or the clustering in particular, has applications in astronomy and particle physics. I think it may have been used in the data analysis of CERN data, the CERN, the Large Hadron Collider, that where they try to figure out whether the Higgs boson particle exists or not by the through the data gathered from the particle collision reactions. Then similarly, it can be used in market segmentations. Further applications can be found on cluster analysis. This cluster analysis link on Wikipedia. So let's take an example of a k-means clustering algorithm. One algorithm for performing clustering, just to understand how it is done in practice. So let's say so the first step is I randomly choose initial cluster centroids. So let's say this is the centroid of first cluster, this is the centroid of second cluster, and this is the centroid of the second cluster. Now, in the second step, we assign each point in our data set to a cluster centroid through the closest distance mechanism. So let's say some of these points are assigned to this cluster centroid, some of these points are assigned to, now the rule is you can assign a point to a cluster centroid only one cluster centroid. So let's say some of these other points are assigned to this cluster centroid, and then let's say some of these points are assigned to this cluster centroid. Now you recompute the cluster centroids as an average of all the training points assigned. So let's say you compute the average x and y of all the points assigned to this cluster, and this cluster. And then the new cluster centroids are recomputed as, so let's say these were the previous cluster centroids, these are the new cluster centroids. And then you repeat the steps 2 and 3 till you get the convergence. Now it should be kept in mind that this algorithm is one of the earliest algorithms. The performance of this algorithm depends quite heavily on the initial cluster centroids as well as the distance measure that is chosen, and it is most likely going to give you a local minima and not the optimum clusters. So you need to repeat this k-means this entire algorithm several times for different initial conditions, and then pick the one which gives you the best distance, minimum distance. Let's move on to view in the interest of time. Let's move on to see what are the different tools used in machine learning. Apache Mahout appears to be the most popular and the most deployed machine learning library. It contains implementations of various recommender systems, clustering, and various algorithms for recommender systems, clustering, and classification algorithms. It is Java based, and it has some algorithms which are Hadoop MapReduce based, as well as it has the normal the single machine implementations. They have recently started Spark based implementations with the aim, and their aim is to build a machine learning domain specific language. So you should be able to express your machine learning task as a set of let's say I want to train using k-means clustering and so on in a very simple manner. This DSL is going to be Scala based, and as you know, as some of you might know, Scala runs on top of JVM. So basically this is the future direction of Mahout. It is stable, widely used in production, and it has community support. Then R is another popular library. It is it has a GNU license that has to be kept in mind, and it has its own language. It is quite popular in the statistics world, and some ports of R run on Hadoop, as well as there is a recent effort to run R on Spark as well. Then Spark itself comes with its own machine learning library. They have two variants. MLlib is their lower layer of machine learning library, and on top of that they have tried to build a higher level library or an abstraction called MLBase. Here they try to run the optimizations like choosing the optimum lambda in the background. So while they give you a model right away, they might keep on refining the model in the background. This is Scala based, this runs on Spark, and it is in memory. It runs, which is an in-memory, and Spark, as you know, is an in-memory distributed cluster computing. Then there are a few more like Weka, which is Java based. It has a GNU license. There is another library someone pointed out recently to me, which is Gopal Wobbit. Sorry. There is a Google Prediction API. This is a cloud based offering from Google, and then you can look up the rest in the Wikipedia link. These are some of the popular implementations of machine learning. As you know, Google speech recognition system, which is embedded in Google Now, and iPhone, iPad, Siri. This is completely based on machine learning and internet search. Basically, they implement the speech recognition in their cloud. They take your voice sample, they send it over the internet, and then they recognize the voice and send it back to the mobile, the recognized text string. Similarly, the natural language processing and the Google Translate, that is also a machine learning, a very prominent real-life machine learning example. Then you have face recognition in cameras and online photos. So you would have seen that in Google Photos, they sometimes tell you, okay, these photos, they sometimes put rectangles on Google and other online photo collections like Flickr. They put rectangles around pictures like faces, and also they can recognize, not only they can recognize faces, they can also recognize the similar faces. So if you label a particular face as, let's say, your face, then it will try to find and automatically label your photos with your faces. Similarly, optical character recognition is also another very prominent use case. Handwriting, and there are some mobile apps that I particularly like. There is one app called MyScript Calculator and a stylus keyboard. They are on Android. And MyScript Calculator, you can just scribble using your fingers, and it recognizes even E, pi, superscript, subscript. It's a beautiful application. Then you have OCR of printed documents and handwriting. This can be this can be very useful in, for example, the document organization systems, where they, after performing the OCR, instead of just maintaining a PDF image copy of the documents, you can make the documents searchable if you perform OCR on those and then index the documents. So these documents then become searchable. Then, of course, as I mentioned previously, automatic tagging of photos based on similar photos. In biology, again, you have like tremendous potential. Using the DNA analysis, it can identify whether a person has a particular disease or not. It can give you a probability of what are the likely diseases you may have in the future whether you are likely to have cardiac disease or not. And then it can also recommend you drugs based on like personalized drugs suitable for your, like for example, you may be allergic to some drugs, so then it will recommend a different type of drug to you for the same disease. So personalized drugs is another application. Then let me conclude the talk with some of the online resources for machine learning. You can take, this is a very beautiful, simple course on Coursera, machine learning by Professor Andrew Ng of Stanford University. Then you have neural networks for machine learning. This is an advanced course. You can also call this as a course on deep learning. This is by Jeffrey Hinton. Then you have another course on Udacity. This was another course that someone recommended to me, in Introduction to Artificial Intelligence. There is a Carnegie. Professor Alex Mola, he teaches Introduction to Machine Learning and also Scalable Machine Learning. He was a research scientist in Yahoo. I think he has moved to Google now. Then there are several books. Pattern Recognition and Machine Learning by Christopher Bishop. Then Machine Learning by Tom Mitchell. I have put a link to this. You can find PDFs of all the books online. I'm not putting these here. Then Artificial Intelligence, a Modern Approach, and Machine Learning in Action. This is an O'Reilly book, I think. And these are several links. You can go through all the answers to this question, how to explain machine learning to a layman or to non-computer science people. And then there are several questions asked on and answers on this topic, machine learning. You have fastml.com. This is a collection of machine learning blogs, I think. Alex Smola, he maintains his own website for like several machine learning resources. This is a very useful website for people who want to do career there in machine learning. Then you have large-scale distributed deep learning networks. This was a conference recently held in Bangalore on big data. This is one of the talks, realizing large-scale distributed deep learning networks. Then there is a recent Spark Summit has a very good collection of talks and papers. There is a tutorial on speech recognition by Rabiner. This is one of the old classics. And then this is a link to the Tesseract library. This has been, Google maintains this optical character recognition library for printed characters, and this is also quite widely used. All right, so with this I conclude my talk.
Yeah, thanks for such an insightful presentation, Kiran. We really thank, on behalf of all presenting, we really thanks to you. Right, before moving to the question answer session, if you can just share that link, video link, that video word lens application, right? So it will be very good for our, it will be very good for our participants.
I will do that. Yeah, actually, I will instead of just the video link, I think I'll upload my presentation.
No, we will upload the presentation on behalf of you. All right.
Okay.
So meanwhile, we will just move to the question answer session. I request you to please read out question as well as their answer, so that all our users will get the commendable insights. Right. So you can go to the chat question tab and you can find the questions.
All right. So the first question is, hi, I am. I'll just read out the question. Hi, I am sophomore at Master of Computer Science. I know theoretical perspective of big data, Hadoop, NoSQL, and just install Cloudera VM. What are the resources to learn actual practical perspective of Hadoop and NoSQL? I don't think this really pertains to machine learning. If you I think there are several resources on the net you can find to learn Hadoop. There is a book on Hadoop called Hadoop in Action. So I think you can pick that up.
Can I request you to go to the question and answer section? There you will find questions.
Okay. Where is the okay? So this was pasted in the chat window.
No, you know, do not need to go in the chat window. You have to go in the question.
Okay.
Questions.
Fine. I think the window is really, really small. One second, let me see if I can maximize this.
Are you able to see the questions?
Yeah, it's in a very small window. Can you help me with those? I'm not able to resize. One second. Okay, fine. Now I can. Yeah. So it popped out. Hi Kiran, do we have? Okay, so the first question is by Sujay Gajula. It says, hi Kiran, do we have open source forums where we can learn to work on machine learning algorithms from scratch? Yes, definitely. I think I have provided some of them in my presentation. I provided sufficient links, I think, to learn machine learning from scratch. I think the best would be you can take the Coursera course. It is quite nicely paced. Second question is, what are the prerequisites for a developer before she starts working in machine learning area? I think it will be best to take the course again. In Mahout the next question is, in Mahout, is there all the package like SNNS, libsvm, GA? Mahout has this is from Jivitesh Shivaswamy. Yes, Mahout does have a lot, has a huge collection. I don't think it has SVM. I don't recollect it has SVM, but it has a large collection of classification, clustering. Also, the algorithms it has is I think fuzzy k-means, fuzzy k-means, then latent Dirichlet allocation. Then in classification, it has one of the prominent ones it has is online gradient descent. So that is the one I recollect having used. Then naive Bayes is another one it has. Okay. Okay, what are the prerequisites for a developer? Okay, we covered that. Sorry. What are the what all mathematical topics one can study for building mathematical models? A topic discussion on fastml.com. Basically, you need to learn linear algebra, somewhat of vector calculus, and I guess that's it to begin with. What is the best way to find the algorithms? Okay, I want to business analytics. Okay, so let me just, what is the best way to find the algorithm? This is the question from Tapas Chakrabarti, is not clear to me. Like which algorithm is he looking into? The next question is, I want to move into business analytics domain. I have got 4 years of business analytics experience. Please suggest me which is the first and foremost tool. I think you can learn R to start with. You can get some theoretical background on statistics and machine learning, and then R. For example, how did we find whether we apply naive
bit louder?
Okay, fine. So, okay. So the next question is, okay, again, I think Tapas Chakravarti has a follow-up question. He is asking, how do we find whether we apply naive Bayes theorem or k-means algorithm? I think that really depends on the data, and if you are expecting like that really depends on the data, and also I think it comes with experience. You also have to try different algorithms to see and test them on the test data to see what's the, I mean, whether it matches with the desired output. It also depends on the data, which is like, for example, if you expect hierarchical topics, you should not really use k-means algorithm. K-means is one of the simplest, and like it doesn't give great answers. It is good to use as a pre-processing step generally, but if clustering is your means, I mean, is the final thing that you want to do, then I think you should definitely look at other algorithms like fuzzy k-means, which gives you hierarchical topics. Then latent Dirichlet allocation is also it is basically a model-based clustering. It gives you the probability distribution of whether a particular feature vector or a document belongs to, I mean, how much probability it belongs to different clusters. So here it is not just that your document belongs to only one cluster. So if your problem is like, if your problem domain is like where you have your feature vectors can belong to multiple clusters at the same time, you should definitely use these other advanced algorithms like latent Dirichlet allocation and fuzzy k-means. Again, I think Mahout in action will give you a good answer on how to pick a given algorithm. Mahout in action, although it's not a comprehensive book on machine learning, I think it has some good practical advice on how to pick different algorithms. Okay, so the next question is, need to really have in-depth understanding of all the algorithms. I think you should definitely have an overview of all the algorithms, although you need not have in-depth understanding. You should definitely have a good understanding of machine learning in general, but not an in-depth understanding of all the algorithms. As long as you understand what they do to your data, like some algorithms treat, like as I said in the clustering, k-means algorithm treats the variance of all the in the feature vector for all the dimensions as same. So it basically treats your clusters as circles. So if the variance is different in different dimensions, then it wouldn't do a good job. Anything else?
So I think we are done with the questions, Kiran. I'm really thankful to you for conducting this webinar. It was indeed a great session. I would like to thank all our participants for their support in making this webinar a success. The recording of this webinar will be available on techgeek.com by tomorrow. Thank you all. Thank you, Kiran. Have a nice day.
Sure. I will put the link shortly, okay, to the video. It's basically you just need to look for the word lens document, word lens app on the Google Play Store.